This lecture talks about a technique that I call the slice absorption method. And really the goal of this is we are looking to solve a very large three-dimensional finite difference frequency domain problem, which we understand has issues because of the scaling. It's a very brute force technique. And there's two approaches to this. We can modify the formulation so that it better accommodates iterative solution, or there is the slice absorption method where we're able to solve sections of the problem independently. And we kind of step through a three-dimensional grid much like we did with scattering matrices and rigorous coupled wave analysis and method of lines. So let's review the formulation of a fully three-dimensional finite difference frequency domain as we've been talking about it. So we start off with a normalized form of Maxwell's equations. We approximate all of the finite differences on a Yee grid, and we get a very simple set of finite difference equations. So if we have 10,000 points in our grid, each one of these equations, take this first one, will be written 10,000 times, and we can cast that in matrix form, and I'm showing all 6 equations in matrix form on the right hand side. Well, we can take this first group of 3 matrix equations and write those in block matrix form, and now this resembles the original curl equation. Remember, the curl of E equals mu times H. So we have a matrix version of the curl operator operating on E equals mu times H. And we take the second set of 3 matrix equations, we build another block matrix equation, and we see we have our second curl equation now in matrix form. Well, now that we have our 2 curl equations, we can substitute one into the other and derive 2 flavors of a matrix wave equation, one in terms of the magnetic field and one in terms of the electric field. So on the left is a reiteration of the matrix curl equations, and then on the right are our 2 possible wave equations, and it's in the form of AX equals 0. And so what I'm going to show is this three-dimensional problem is really too big to solve by a direct solution like an LU decomposition. So let's look at a typical grid. A typical grid for finite difference frequency domain might be 20 points by 20 points in the transverse directions, and maybe 100 points in the longitudinal direction. The reality is we'll probably need more points than that. So this is a pretty small grid, but it'll give you a good idea of how things scale. So we have 20 by 20 by 100 points. That is a total of 40,000 points in our grid. That means to store EX, EY, and EZ, we have 120,000 complex numbers that we need to store. Well, reality is we store both components of a complex number separately, and in the end we need 240,000 real floating point numbers to store all of the field information on this grid. Well, then if we come up with a matrix that is manipulating fields on that grid, that will be roughly 120,000 by 120,000 complex numbers. So if we add up how many elements are in matrices these size, it's over 14 billion complex numbers. Or like we did before, it's almost 30 billion real numbers that we have to solve. So that we have to store. So if we stored this as a full matrix, that would be about 215 gigabytes. That's a lot. If we look at just one field component, that's 40,000 complex numbers. But since we're storing this in a column vector and not a big matrix, it's only 625 kilobytes. So in fact, storing the fields is not the problem. It's the matrices that are manipulating those fields. That's the problem. If we look at one of our derivative operators for this grid, that's 40,000 by 40,000 complex numbers. If we stored it as a full matrix, it's 24 gigabytes. Turns out the density, only 0.005% of the numbers in DX for a grid this size actually contains numbers. So if we store it as a sparse matrix, it's only 1.5 megabytes. That's like 5 orders of magnitude smaller. So one moral to come away with, we definitely want to work with sparse matrices. And our curl operator would be the 215 gigabytes. If we store it as a sparse, it's only 8.2 megabytes. Well, one thing to come away with, if we are using a direct solution, it ends up forming an upper triangular matrix, which is about half the size of this full matrix. And it turns out we will need about 110 gigabytes to solve this problem directly with a LU decomposition or something like that. That is not feasible. And like I mentioned before, we have two possibilities here. We can solve it iteratively, or we can solve it using the slice absorption method. We've talked a bit about iterative solutions. This lecture is on the slice absorption method technique. So I want to step you through what I call matrix ordering. And here's where we look at the order that we've listed the electric fields in our column vectors and how that relates back to our wave matrix. So we have a matrix wave equation that I'll call omega times E equals 0. And here's this big omega matrix. That's the wave matrix. And if we refer back to the original block matrix equation, it would look something like this, where this big 3 by 3 block matrix is the omega matrix. It's operating on this column vector of column vectors, EX, EY, and EZ, and everything equals 0. We know we need a source in here, but let's ignore that for right now. Just look at how things are ordered. So we raster through the entire three-dimensional grid, and we will list all of the EX components in a single file line. And the trick here is we raster first along X, then Y, then Z. And we do that for the X components, then we do it again for the Y components, and then we do it again for the Z components. So a way to visualize the composite vector is that the top third is this column vector of all the EX components, the middle third is a column vector of all the EY components, and the bottom third is a column vector of all the EZ components. Now what we want to do is reorder the order that these electric fields appear. So we'll just call that a reorder operation. And we're going to do this in a way that we list the X, Y, and Z components of the first point, and then X, Y, Z of the second point, X, Y, Z of another point, and so on. So these end up becoming interlaced and mixed. But we do gradually raster through the grid going XYZ, XYZ, XYZ components. So now let's see what happens if we reorder our wave matrix omega by the same procedure. Something sort of magical happens. If we do that reordering, it turns out our omega E equals 0 or equals F equation becomes something that has a block tridiagonal form. And here, this bold E1 are all of the X, Y, and Z components in the first layer of our three-dimensional grid. So here's our first layer. I'm outlining it with the cursor. And all of the X, Y, Z components, remember they're interlaced, X, Y, Z, X, Y, Z, X, Y, Z. They fall all in this column vector E1. So E1 contains all of the fields in slice 1. E2 contains all the fields in slice 2, and so on. And then these F's contain the source conditions associated with each slice. Now, however we reorder this column vector, we also reorder our wave matrix, swapping rows and columns according to the same rule that we swapped rows in this column vector. When we do that, it turns out we only have non-zero elements along the center diagonal in what's called a block tridiagonal form, where we can identify 3 square matrices in a row that are associated with each slice. And what's neat is we can now ascribe physical meaning to these. The A matrix describes coupling from whatever slice we're talking about to the previous slice. The C matrix describes coupling to the following slice. And then the B matrix describes coupling within the slice itself. Now, I don't think we could derive any more meaning than that. We just know that for a given slice, A describes coupling to the previous slice, B describes coupling within the slice, C describes coupling to the following slice, and F is a source condition that may be incorporated into that slice. We didn't have this block tridiagonal form for our original, the original way we formulated finite difference frequency domain. When we reordered it, now we do have this block tridiagonal form. Now, in some sense, the slice absorption method is just an efficient solver for block tridiagonal matrices. The additional thing I think that goes above and beyond just a tridiagonal solver is that we look at these matrices independently. We ascribe meaning to them, which lets us incorporate some neat boundary conditions. It's very easy to incorporate sources and do some other things. So it is a block tridiagonal solver, but we're only calculating, a few slices at a time, and we're sort of like when we did the scattering matrix, we went one layer at a time. There's a similar algorithm here that lets us go one slice at a time and progress through the entire grid and not have to solve the whole thing entirely. So, as I mentioned, each slice has a set of matrices associated with it. So let's look at slice 2. The slice equation associated with slice 2 is an A2 times E1, this is the electric fields before slice 2, plus B2 times E2, these are the electric fields in the slice we're talking about, plus C2 times E3, those are the fields in the following slice, equals potentially some source condition that has been incorporated into that slice. So every slice has an A, B, C, and potentially an F associated with it. The only exceptions are the first and last slice. The first slice does not have an A matrix. We can calculate it, but it's not used. And the last slice does not have a C matrix. We could calculate it, but we don't use it to solve for the fields. So the A, B, C, and F, we will call the slice data. So now that we understand a bit how a three-dimensional finite difference frequency domain is formulated, how we can reorder the fields, and suddenly we get this block tridiagonal symmetry in our matrices, which lets us look at one slice at a time and start ascribing physical meaning, now let's talk about the slice absorption method proper. So here's one way that we can calculate the slice data for a particular slice. Let's say we're interested in calculating the slice data for slice 2, what I'm showing in blue here. So one thing we could do is build a three-dimensional grid and construct a traditional finite difference frequency domain wave matrix for 3 adjacent slices. That's nx by ny by 3. So it's just 3 tall. And we construct the standard finite difference frequency domain wave matrix and potentially a source. Then we reorder those. And after we reorder, that gives us our wave matrix and the entire matrix equation this block tridiagonal form. Well, we can read from that center block row all of our slice data, A, B, C, and F. And we can pull those off and discard everything else that was associated with this. So now we know how to calculate the data for a slice. Now we need to talk about the absorbing part. This is the thing that lets us go one slice at a time. So let's just suppose we had a stack of 3 slices, and each of these has a slice equation. What we want to do is somehow algebraically eliminate this middle slice and absorb all that information into the top and the bottom slice. So we start off with our 3 slice equations, and we want to eliminate the middle one. So what we'll do is we'll take that center slice equation and solve it for the electric field in that slice. Then we'll take this expression for the electric field in this ith slice, if you will, and we will substitute it in to where that appears in the first and third equations. When we do that, we eliminate any reference to E sub I. We're only referencing other slices now, and we've eliminated it or absorbed it. So we substitute that in, And now we have some algebra ahead of us. And here's where we end up after we do the algebra and multiply everything out and collect coefficients. Now notice this, for the most part, is in the same form as our typical slice equations. It's just that the slice data is updated. It's slightly different because the slice data associated with the first and third slices has now absorbed information from that second slice. So I envision the absorption process something like this. We'll start off with a stack of 3 slices, absorb the middle slice. We have slice data for the first and third slice, but no longer for this one. It's been absorbed into the first and second, and we can throw out any information associated with what we had of the blue slice. So pulling it all together, here's a summary of the slice absorption procedure. We had 3 slice equations with 3 adjacent slices. We wanted to eliminate this middle one. We have updated slice equations for the first and third slices, and here's how we calculate all of the updated slice data. At this point, we can eliminate all of the data associated with the ith slice that has been absorbed into the first and third. So the second slice can be gone. One thing we may want to do sometimes, which simplifies things a little bit, is not necessarily eliminate a slice in the middle of a stack. Maybe we have the slice at the very top that we want to absorb and work downward. We don't really care what's above it because that's the top of our grid. So we would have the top 2 slice equations. Now notice this is referencing a field from outside the grid, so we'll write this term here, but the reality is we don't use it, but at least mathematically we can write it. So we have the slice equations for the 2 top slices in our 3-dimensional grid. Well, what we'll do is we'll take this first slice and solve it for the field in that slice, and then substitute it into the second equation. So now what we have is an updated equation for the second slice, where the information from the first slice has been absorbed into it. So here's how we calculate all of the slice data. Now at this point, the slice data for the second slice now is referencing a field from outside the grid, so hopefully we don't need this term when we solve it, and in fact we won't, and you'll see why. We can do a similar thing from the bottom of the grid. Let's say these are the last 2 slice equations. Well, we can solve this equation for the field in the last slice, which is E3 in this case. Substitute in up here, and now we have a modified equation for the second to last slice that has absorbed information from the last slice into it, and here's how we calculate the updated slice information. So this slide and the last slide lets us work in from the edges. The slide before that let us absorb an interior slice. So let's say we have a large stack. We have a 3-dimensional grid. How do we step through this one slice at a time? Well, we'll calculate 2 slices. We'll calculate a third slice. At this point, we can eliminate the middle slice. We're back to 2 slices. We calculate the 4th slice. Suddenly, this third slice becomes the new middle slice, and we can absorb it now into the 4th and 1st. And so on. We keep doing this, and we work our way through an entire stack of slices, and we can pretty quickly work through a large 3-dimensional grid this way. So here is an animation of the slice absorption method, and what is highlighted in green is the slice data that has been calculated, and when it sort of expands and contracts, that is conveying that we're absorbing information, and then you can see the slice data kind of go transparent and then white. The white means we've eliminated the data from the memory. So we just work through a stack of slices this way, and in a way it's similar to what we did with scattering matrices. But here we have to have more than one slice in memory to do the absorption, whereas scattering matrices, we could calculate scattering matrices just for a single layer. Although we still needed the second layer to update scattering matrices. Now, when we talked about scattering matrices, we talked about a fancy cascading and doubling algorithm where we essentially step through a unit cell that could be rather complex. We'd have a single scattering matrix describing that, and then we started star producting that star matrix with itself, and we eventually doubled. First we had a scattering matrix of one unit cell. When you star it with itself, you have a single scattering matrix describing 2 unit cells. Star it with itself, you're describing 4 unit cells, 8, 16, 32, 64, and we really quickly describe many, many layers. There's a similar thing that we can do here. So imagine what we did on a previous slide where we had a large stack of slices, and we progressed through and absorb all the interior slices. So we're just left with the first and last, perhaps of some unit cell. Well, we can take these 2 slice equations now, we can stack them on top of each other. And then we absorb the interior slices with 2 absorption procedures. Now we have 2 slice equations that really are describing 2 unit cells between them. We can take these slice equations, stack them onto themselves, absorb the 2 interior slices. Now we're describing 4 unit cells, and 4, 8, 16, 32, a similar type of thing. So we can very efficiently describe very large structures this way. Okay, now we need to learn how to incorporate a source. So we will set this up just like we did for a 3-dimensional finite difference time domain, and just like we did when we briefly talked about a 3-dimensional finite difference frequency domain. And I'm also showing here a PML. We absolutely can use a PML in this method, no problems there. I am also going to show you a different boundary condition that I think works a bit better than the PML because it doesn't require the spacer regions and it can handle the evanescent fields really well. And it doesn't require needing 20 cells or so. It can be just a single cell. But otherwise the grid is really constructed exactly the same, and we absolutely could incorporate a PML, no problems. So just like before, we know when we adopt the total field scattered field scheme that the finite difference equations on the interface of that total field scattered field region, those finite difference equations contain terms from the other side. So for example, here is a slice equation that exists in the scattered field. However, it contains an electric field from the total field side. That's not compatible. We have to fix that. Likewise, we have a slice equation from the total field side that contains a term from the scattered field side, and we have to fix that. So just for simplicity, I'm calling these slices 1 and 2, but the reality is it's probably slices 20 and 21 or something like that. But we'll just call them 1 and 2. Those are the ones spanning the interface between the total field and scattered field. Okay, so in the first equation, in the scattered field, the problem term is E2. All of the terms in this equation are expecting scattered field quantities, yet we have a total field term. So we have to subtract the source from it. So here's the new slice equation for equation 1, where we're subtracting the source. And since we're talking about the electric field in the second slice, this is the source in the second slice. Likewise, this equation in the total field, we have an electric field from the scattered field side. Well, we need to make the scattered field look like a total field, and we do that by adding the source to it. And we're also adding the source in that slice number 1. Well, we just rearrange the equations, and what we see is that on the left side, nothing changes. We have the exact same slice data. However, on the right-hand side, what used to be 0 now has source terms there. And so for a total field scatter field source, we end up having to modify 2 slices, the 2 that are spanning that interface, and we use the slice data to calculate those column vectors that need to be on the right-hand side. So the procedure here is we'll calculate the source in the first slice, calculate the field in the second slice, use the slice data then to calculate the source terms F1 and F2 that we then insert as the slice data into the slices spanning the interface between the total field and scatter field. Okay, so how do we calculate the source terms? Well, this shouldn't surprise you. We are going to have the x component of the source across a three-dimensional grid, however, reshaped into a column vector. Same thing for the y component, and the same thing for the z component. So this px, py, and pz, these are just single scalar numbers that we calculate just like what we did in the transfer matrix method, and then again in rigorous coupled wave analysis. Well, if we know the field in the first slice, it's just a single plane wave. That's what we're doing here. So we immediately know what the field is in the second slice. It's the field in the first slice plus whatever phase that source would accumulate going from the first to the second slice. So the reality is we really only need the source in one plane, and we can calculate the other one directly from it. Okay, so instead of using a PML, which requires the use of, let's say, 20 cells plus even a spacer region, that's a lot of real estate in a three-dimensional grid. There's another type of boundary condition that I'm calling a transparent boundary condition that we can use. Another packages, sometimes they may call it the Floquet boundary condition, but we can do this in one layer and it works perfectly. It handles evanescent fields, so we don't need the spacer regions, and it just works really, really well. So in order for us to implement this transparent boundary condition in the simplest possible way, and there's fixes to some of the things I'm going to talk about, but what we're going to do requires that our outer boundaries are inside homogeneous materials, and that's really what we've been doing so far. That's not too big of a deal. The other thing is it requires that energy propagating in the slices is only going in a single direction. So at the top of the grid, energy can only be going up and out. At the bottom of the grid, it can only be going down and out. And because of how we constructed our total field scatter field, we really are ensured that that is the case. So that's not a problem. As I mentioned, this transparent boundary condition handles evanescent fields perfectly, so we don't need the spacer regions. In fact, when you have zero spacer regions, you can that could be so small that you may actually want to add that back in just to visualize your fields better. We're going to construct a matrix operator, sort of like what we did for derivative operators, convolution matrices. We're going to construct one that builds FFT operators for doing fast Fourier transforms. In fact, it may be improper to call it a fast Fourier transform. We probably should call it a discrete Fourier transform. They're slow to construct, and that's the Achilles heel of this. And I think that can be improved, but that's the choke point here. Okay, so given the field in a particular slice, we know, since we're in real space, that we could have some angle of incidence, and in order to Fourier transform that, we need to remove the phase tilt, so we really just get the amplitude portion of that. So given the electric field in a slice, we can construct a big ugly square matrix. So if we multiply that times the electric field, we'll get the amplitude portion of the electric field, and we get rid of that plane wave phase term from the Bloch-Floquet theorem. So how do we calculate that? Well, imagine a scalar tilt thing where we construct the conjugate phase across the grid, we diagonalize that, and then we add that phase for all three components. We make a big block diagonal matrix, and then we reorder it. Then it's compatible with how we've ordered the electric fields here. So when we multiply T times E, we simply get the amplitude portions back. And this is the conjugate phase. So we multiply this in, it will remove that plane wave phase tilt term. The next thing we need is a matrix that does Fourier transforms. So given this amplitude portion, that is the thing that's periodic. Now we're going to build a big ugly square matrix that computes a Fourier transform, a discrete Fourier transform. So F times A will then give us S, which is amplitudes of spatial harmonics. And this will be the same amplitudes that we would have if we were doing rigorous coupled wave analysis, for example. So here's how we define a two-dimensional discrete Fourier transform, and it's actually from this that tells us how to build this Fourier transform matrix. So for a single scalar field, we'd build an F prime. For our 3D vector fields, we make a block diagonal matrix of these F primes and then reorder that. And now we have an F such that if we said f times the amplitude term, we would get the amplitudes of our spatial harmonics. Then we'll have our spatial harmonics in one slice. What we'll want to do now is propagate them to an adjacent slice. So they're going to travel a distance of delta z. So given the field in slice I, we multiply this by some phase accumulator, z sub I, it will then propagate all of these spatial harmonics to the next slice, I plus 1. Well, if we had a single scalar field, that's z prime, here's how much phase we need to add to each of our spatial harmonics, and we're getting the z components from the dispersion relation. That's z prime just for a single scalar. So then we make a block diagonal matrix from our z primes, and then reorder that. And now we have a z matrix such that we can propagate the spatial harmonics from one slice to the next. Okay, now we need to put these together. Really what we wanted to do is we wanted to be able to calculate the field in a following slice, given the field in one slice, by multiplying by some propagator p. So given the field in the ith slice, we multiply by p, we immediately get the field in the next slice. So how do we do that? Well, the first thing we need to do is remove the phase tilt. So we will pre-multiply e by this tilt operator. Then we want to Fourier transform the fields. So we pre-multiply this by the Fourier transform operator. Then we want to add phase to our spatial harmonics. After we Fourier transform, we have spatial harmonics. We add phase to them. So now we have the amplitudes of the spatial harmonics in the next slice. Well, we want to go back to real space now, so we inverse Fourier transform by pre-dividing. And then we want to incorporate the tilt again by pre-dividing by the tilt operator. So if we put all this together, our propagator, which will propagate from slice I to I plus 1, is simply all this. It's a combination of these three matrix operators that we just constructed. Okay, now finally the boundary condition. That's just describing the way we'll calculate this propagator. So let's say we're at the top of the grid and we have this term here, E sub 0. Well, this doesn't exist. It's outside of the grid. We have no way of getting it. However, if the energy at the top of the grid, or the power at the top of the grid, is only traveling upward and outward, then we can calculate E sub 0 from E sub 1 using a propagator. So we'll have a propagator for the reflection side that will let us calculate E sub 0 from E sub 1. E sub 1 does exist. So if we take this expression for E0 and we plug it in up here to get rid of E0, suddenly the A from our matrix equation drops out and we have a modified slice equation. No longer contains A, but B is slightly updated and it contains this propagator. It's the old B slice data plus A1 times P ref. So at this point, we no longer need A1. We've incorporated this transparent boundary condition simply by modifying B in that outward slice equation. A very, very similar thing happens at the bottom of the grid. We have this reference to the electric field at slice n plus 1, but we're only storing n slices. This doesn't exist. But we can calculate the field outside of the grid based on the field inside the grid by multiplying by this propagator on the transmitted side. So now we take this expression for E sub n plus 1, plug it in up here, and in fact that whole term drops off. We modify our slice equation, and again this transparent boundary condition really just modifies the B matrix of the slice data. We have the old one plus this correction term, Cn times Ptrn, which incorporates this transparent boundary condition. Once we've done this, we no longer need the C matrix in the last slice. Okay, now we have to tie all this together. So if we've done our job, if we had a PML, let's say, we'll probably progress from the outside of the grid up to where we want to record our reflected fields. We'll do the same at the bottom. We'll progress upward to where we want to record our fields here. Then between the two planes, we'll do our standard slice absorption. We'll go one slice at a time, absorb, 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 until finally we're just left with two slices in the record planes. And we have our two slice equations. And the primes here indicate that all the information from the other slices have been absorbed here algebraically. Well, now, remember this, A1 prime and C prime really aren't needed. We kept track of them up till now, but now we just throw them out. We don't need them. Now we build a final 2x2 matrix, and this is a heck of a lot smaller than the full three-dimensional matrix. This is very easily solvable. And you'll notice there is no A for the first slice, and there is no C for the second slice. We don't need those at this point. If we solve this matrix equation, we will then calculate the fields in the two remaining slices, which hopefully we've chosen to be our reflection and transmission record planes. So we solve for those fields by backward division. That's up here. Then if we take this EREF and unreorder it, now we're back to what we would have gotten had we solved the full finite difference frequency domain just in those slices. And we also reorder on the transmitted side. So we have X, Y, and Z components now on both sides. And now it's very straightforward to calculate diffraction efficiencies. Now what's neat, since we've already constructed tilt and Fourier transform operators, we can use those to very quickly calculate the amplitudes of the spatial harmonics. We just use these two equations, and now we have the amplitudes of the spatial harmonics on either side. Then it's a real easy thing to calculate diffraction efficiencies of the reflected or transmitted modes using the exact same equations that we've been using. We can also talk about a Fourier space slice absorption method. We've been talking about a real space and essentially replacing finite difference frequency domain. Well, let's think of it this way. Here we're showing a three-dimensional finite difference frequency domain grid. What if we thought of this more as like rigorous coupled wave analysis, where inside each one of these slices, we don't want to know the field at discrete points, we want to know the amplitudes in a plane wave expansion. So each slice has its own little plane wave expansion. This would be a Fourier space slice absorption method. We'll still handle the Z direction with finite differences, but X and Y we're going to handle with the discrete Fourier transform. So what we had before for the real space slice absorption method was this. Now in Fourier space, we have kx and ky instead of dx and dy, but we still have the z derivatives. And over here, these aren't diagonal matrices anymore. These are our convolution matrices, which we can construct with our convmat function we learned several lectures ago. So here's one area where we applied this method. We were direct laser writing photonic crystals by a process called multi-photon direct laser writing. And the reference at the bottom if you want to read about that. So we were testing these inside of a Fourier transform infrared spectrometer, an FTIR, and we wanted to duplicate the simulation results. And so I used the slice absorption method to do this. Why did I use that? Because if we look at this lattice, it has smooth curves that I wanted to resolve. So using a technique like rigorous coupled wave analysis would have required many, many layers, and the eigensystem computation to each of those layers was rather extensive. So I wanted to avoid that. And so went with the slice absorption method instead, because we can progress one layer at a time, but there's no eigenvalue computation in each of those layers. It's just algebra. It's roughly as computationally intense as combining scattering matrices. So we have that, but we don't have to do the eigenvalue computation. So here's a Fourier transform infrared spectrometer. Now, interestingly, it does not illuminate the lattice with a perfect plane wave. It's using something called a Cassegrain optic, and in fact, it illuminates it with a conical beam that has no energy in the middle. And for this particular one we were doing, the cone angle of this inner missing energy region was 16 degrees, and roughly the outside was 33 degrees. But it illuminated the lattice with this entire cone of angles. So one of the tricks was, if we want to duplicate our measured results, we have to duplicate how the device was measured. So in fact, we have to incorporate that type of beam into our model. The other thing that what most people would do is they would look at this lattice and they would approximate it with something that's sort of idealized. Now, something like this, being blocky and binary, is probably very efficiently analyzed with rigorous coupled wave analysis, probably better than the slice absorption method. However, this isn't the real geometry of the lattice. Instead, it looks much more like something like this. And this was predicted by actually modeling the multi-photon direct laser writing process. So, but that's very volumetrically complex, would require a lot more layers than what we're showing on the left. I think rigorous coupled wave analysis will become bogged down, so I used the slice absorption method instead. So here's how I stored it in memory. I really just stored essentially, I don't know what this is, maybe a total of 2 periods. So there's a half period up here, a half period down here, and here's just 1 period. Now ultimately this lattice was something like 6 or 7 unit cells tall, but we don't have to store all 6 or 7 of those unit cells. We just store 1, and we'll do that cascading and doubling algorithm we talked about to incorporate all of them. So, modeling this idealized geometry, we get what I'm showing in the blue line. The measured results is this black line. That came out of the Fourier transform infrared spectrometer. But if we idealize the geometry, this blue line is really about as best as we can get. And I did an equivalent fill fraction here to get it close. When we account for the realistic geometry and also account for that weird conical beam that has no energy in the middle, when we do that, we actually simulate something that's a virtual overlay with what we've measured. And that's really, really incredible. It's very rare to see that. But we represented the geometry very accurately, and we also represented how the thing was measured very accurately in the model. We didn't just assume a perfect plane wave. So the next thing was to metallize these lattices using some kind of electrolysis deposition process. And we wanted to model that. Interestingly, at the same time, there was another research group that was teamed with a company called Lumerical, and they were doing a similar thing. They were coating photonic crystals made by direct laser writing and simulating that. Well, their measured results are shown here in the red and black line. The simulated results are in the blue line, and this is actually published, and here's where they published that. And in my mind, that's not a close match at all. So what were they missing? When we deposited metal on top of ours, here's our experiment versus simulated. The red line here is our measured, and the black line is the simulated. It's not perfect, but is a heck of a lot better than what we saw on the previous slide. So clearly, there's something that we are accounting for that the other team was not. So here's a side-by-side comparison. I think we did strikingly better here. So what was their big mistake? Well, remember, we are modeling a periodic structure. This is a photonic crystal, and so it's a grating, and any periodic structure diffracts. So we'll have a zero order mode, and we'll have these higher order modes. It turns out, inside of in this infrared Fourier transform spectrometer, all of these higher order modes got cut off. It only really measures this zero order mode. So one of the reasons I was able to duplicate our measure results so well is because I took this into account, and I only accounted for the zero order reflected energy. I ignored the rest because how we measured it ignored the rest, and that let us get the really good results. That, in addition to accounting for the beam shape from the Cassegrain optic. So the combination of the two, we got a virtual overlay with the measured results. And the reason, in my opinion, that that's good, that means we understand all of the physics that's happening. So that's it for the slice absorption method.